we introduce the control theory, so the control theory module of this course. And we have seen briefly that what we are going to do is to basically determine the dynamic equation of the attitude of the spacecraft. So briefly, I recalled here how to determine the attitude equations. So basically here you have the torque that is equal to the time variation of the angular momentum of the spacecraft expressed in the body reference frame. So that's the reason why you have an additional term that is given by the angular velocity. So on the angular velocity of the body frame with respect to the inertial reference frame. But you have to be aware that this omega bi is indeed expressed also in the body reference frame. So what I mean here is that if you go to the next slide, if we want to determine omega bi in the body, so the body reference frame angular velocity with respect to the inertial reference frame expressed in the body reference frame coordinates, we can use the omega of the body reference frame with respect to the orbital reference frame, for example, and sum this angular velocity to the angular velocity of the reference frame, of the orbital reference frame with respect to the inertial reference frame. We have to be careful about that because so in order to determine this omega bi, we are expressing both spin rates in the body reference frame. So that's the reason why you see here the elements xb, yb, and zeta b that are the vectors of the reference frame of the spacecraft, which is reported here. And so in this figure, you can see indeed the reference frame of the body, of the orbital reference frame with a 0 subscript, and also the inertial reference frame. So yesterday we indeed computed the angular velocity of the reference frame of the orbital reference frame. So this is the angular velocity of the orbital reference frame with respect to inertial reference frame, also expressed in the body frame. So we are reporting the angular velocity of two reference frames in a third frame. So what we have done here, we have the value of the angular velocity of the orbital reference frame with respect to the inertial reference frame expressed to the orbital reference frame. And in order to have that in the body reference frame, we have to multiply this vector by the orientation matrix that goes from the reference frame, from the orbital reference frame to the body frame. So here is the first time that we are assuming for small angles. So this rotation matrix can be indeed approximated to this rotation matrix in which each element is given by the angles of between the body frame and the orbital reference frame. So today I'm going to show you the stability of the spacecraft. First of all, with a theoretical approach, but afterwards I'm going to show you a MATLAB program that I implemented to explain from an academic purpose how we are able to determine the stability of the spacecraft. So the main problem here is that we are trying to linearize the dynamical equations of the attitude in order to basically have a quick integration of those angles. So that's the reason why here we are assuming small angles. And if you do so, you can see indeed in the last, so at the end, in this left, bottom left of the slide, that you are able, now you have the omega given by, so the angular velocity of the orbital reference frame with respect to the inertial reference frame, that is given by this vector that you can obtain by multiplying this matrix to this vector here. And the other thing is that we assumed that the body frame is moving, so is rotating with respect to the orbital reference frame with velocity p, q, and r. But since we are assuming small angle approximation, what we can do here is that p, q, and r are equal exactly to the phi angle, so the roll angle. Q is equal to the to theta dot, and r is equal to psi dot, so the yaw angle. So these p, q, and r are known because we are assuming small angle approximation. Well, by doing this approach, we are able now to express omega bi, the one that is in the Euler equations, in this simple form. So we have everything in terms of the roll, pitch, and yaw angle axis. So we are able to express these nonlinear second order differential equation in a three set of equations that are linear and are written with respect, so with respect to the roll, the pitch, the roll, the yaw, and pitch angle. So what we have written here, these expression of the angular velocity with respect to the roll, pitch, and yaw angles can be also computed for the time derivative of the spin angular rate. So what we are doing here, we are doing the partial derivative over time of omega x, omega y, and omega z. So you can find that this expression is indeed phi dot dot minus omega 0. Yes, sir. I'm using a tablet to write and the laser pointer from the computer. So if you don't see the laser pointer, let me know, because sometimes I have to switch between the two. So the three set of equations, the two set of equations, okay. The two sets of equations now are well suited to substitute omega dot and omega in the original formulation of the dynamical equations. So that the final representation of the dynamical equations of the attitude is written here. So I don't want to basically spend too much time on that, because I'm pretty sure that you already have seen those formulations. But I think it is important to know what are the assumptions that you do in order to determine this simplified set of equations. Because now what we are going to do is indeed to see when the spacecraft is stable and when the spacecraft is not stable. Of course, the stability of the spacecraft is studied by assuming one of the main perturbation that you have, the gravity gradient. So the gravity gradient here will be used to stabilize the spacecraft and so not to act as a perturbing torque. So what we have in this equation, in the right side, you have the variation of the angles in time for the spin rate and the acceleration due to c dot dot, phi dot dot, c dot dot, and t dot dot. And you have on your left side the disturbance that we are also going to see carefully, because of course the stability of the spacecraft should be studied with the homogeneous that is associated with this set of equations. But we have to see, for example, that when we have a disturbance that is acting on the spacecraft, that will, what kind of consequences will be for our attitude control of the spacecraft. So we have to be careful, for example, that if we have a disturbance, this disturbance is not going to change the orientation of the spacecraft body reference frame with the angles that are too large compared to the orbital reference frame. Because if that disturbance is too large, this set of equation will be completely, will not be valid anymore, and we have to go back to the original set of equations. So these equations, as I said, are valid only if you are assuming small angle variations from the body frame to the orbital reference frame. So small roll, pitch, and yaw angles. The main advantage of this representation is indeed, you can see that the first two equations, so the roll and the yaw axis, are coupled. So basically there are terms that depends on phi and psi for both equations. So in the first equation, you can see that you have terms given that are related to psi dot. So the angular velocity in the yaw direction. In the second equation, you have phi dot. So you have the roll, the angular variation in the roll direction. However, the third equation, the pitch axis, so the one that is orthogonal to the orbital plane, because another important assumption that we are doing here is that we are assuming a circular orbit. That's the reason why you have omega 0. This third equation is fully decoupled from roll and yaw dynamics. And this is a main advantage for this representation, because what we can do indeed here is to treat these axes separately from the other two. So let's do a simpler example. Assuming that instead of a spacecraft that is orbiting Earth, you are basically going to have a tether. A space tether is basically a long line that could be a few meters that has the properties to have one of the moment of inertia equal to 0. So the moment of inertia along the axis of this tether is equal to 0. So let's assume that the principal axis of the tether will be with zeta along the axis of the tether. So it will be Ez equal to 0. And of course, you have that Ix and Iy will be identical because the tether is symmetric with respect to that plane. So you have that Ix and Iy are equal to I. Well, here we can indeed have a first interesting result for the stability of an object that is orbiting around the Earth and with the only effect of the gravity gradient. What you can see here, since I zeta is equal to 0, what you have indeed, so this term is fully 0, and also this one, because you also have that the moment of inertia along y and along x are identical. So what you have at the end, that you can even have a simplified equation for these. So basically just two equations, because you don't have any control on the y-axis, because you are assuming, for example, so you're assuming here that the z direction of the body is going to be aligned to the y-axis. So you can see that for this configuration of the moment of inertia, since you don't have any inertia of the body in this direction, the gravity gradient doesn't give you any contribution. And this is an important result because it's going to be valid also for spacecraft, because usually the moment of inertia along the z-axis is smaller compared to the others, for the reason that we are going to explain afterwards. So the first result here is that if we have a space tether with the axis aligned to the orbital y-axis, you don't have any control from the gravity gradient. The other two components, so the roll and pitch, will have a trend that is close to an oscillatory trend. So if you have initial angle phi or initial angle theta, that give you an oscillation of those angles with a frequency that is given by the orbital period of the spacecraft. So you have to be careful here that we are assuming that, for example, the disturbance is equal to 0, but also that the angle between the body and the orbital frame is small. So in that case, indeed, what happens if you have the configuration that I show you on the top right is that the tether is going to have to act as a pendulum. So oscillates around the x and y direction. Okay, so this is a space tether, but what we want to do is indeed... Prego, prego.
Scusi, ma io non ho ben capito perché t di z lo trascuriamo.
No, okay. So the question is why we are neglecting TD of Z. So the main result that we have to see here is what the gravity gradient is giving to us. So we are basically saying that the contribution of the gravity gradient is 0. So it means that if you have a perturbation along the zeta axis, basically the tether will start to rotate indefinitely along these axes. If you have, for example, a constant torque, you're going to have a constant acceleration of the tether along the axis. So the main purpose here is to show you that the gravity gradient is not going to give you any counter reaction to the disturbance. So we're not neglecting that. We are only saying that if we don't have any disturbances in all the direction, so also in x and y, what happened here is that the phi and theta will oscillate with these law here. The zeta, if you don't have any perturbation, will remain fixed. In case you have perturbation, of course, the gravity gradient is not going to give you any additional counterreaction to the disturbance. But that will be clear later, because here, of course, if you have a tether that is going to rotate along its own axis, it doesn't matter for you because it's a tether, so it can also rotate along its axis, right? So it would be much more interesting when we're going to deal with the spacecraft. Okay, so what I'm going to do here, if you look at the original set of slides, you have a lot of discussions in the Laplace domain, so using the Laplace transform. I tried to simplify that slides because I think that the main important concept that you have to get from those lectures is that you need to know what are the conditions, so what are the design requirements that you have to do to determine a stable spacecraft. So we are going to look at the stability of the spacecraft briefly using also the Laplace domain, but also using an additional approach that basically give you exactly the same results, but you're able to see the same problem with two possible solutions. So the main goal here is to find basically what are the configurations of the spacecraft that give you stability in the three directions. So the pitch, roll, yaw, and axis. As I said, the main problem here is that we have seen that the pitch axis is fully decoupled from the first two. The first two equations are fully coupled. So it means that when we want to determine the stability of these two axes, we need to use these two equations together. So let's start with the first one, that is the easiest one. So the pitch dynamics. Before going to that, I included in these slides a brief recap of what is a Laplace transform. Why we need to do Laplace transform? Because in order to determine the stability of the system, we need to determine, so the Laplace transform has the advantage to transform those differential equations in algebraic equations. So we are able to have the characteristic equations of those differential equations that give you information on the poles of the solutions. So it means that we are able to understand if the system is going to converge or diverge, so if it is going to provide a stable or unstable solution. So the next slides are always with the blue upper triangle, because I'm not really slides for your for this course. There should be concepts already known for other courses, but since these concepts are important for this part, in the next couple of slides you have a recap of the Laplace transform properties. So the main properties in the first slide here is to take this second order differential equation and transform from the time domain to the Laplace domain. The main reason why we do so is because, as I said, what we are going to see is, for example, the characteristic equation that give you the poles of the solution. But it's also important because if you want to, for example, know a direct response of a system, in the Laplace domain, you have something that is called the transfer function. This concept will be a little bit clearer when we're going to deal with the active control. So here, the main important thing is that you have to know that if you do the Laplace transform of a function over time, that will be transformed. So you need to do the integral of e, the exponential minus st f dt in the t, and you have this final expression that you can substitute in your initial differential equation. So one important property, as I said, is to transform the differential equation to an algebraic equation. So if you do the Laplace transform of the time derivative of f, you can see that that will be transformed in Ls times the Laplace transform of f dt minus f0. If you have the second partial derivative, you do the same, and you can see that if you have the second partial derivative over time, you have s squared. So if you substitute these in the second order differential equation, you transform this differential equation in an algebraic equation. Here, as I said, are some concepts important to better understand how the Laplace transform works. One of the main important is indeed to check if there exists a Laplace transform. And there is this theorem that says that the Laplace transform of a function ft exists only if you have this condition. So it is piecewise continuous in this bound. So this is only for your information in order to know why and when the Laplace transform exists. So the main concept that you have to keep in your mind is indeed the transformation from the time domain to the Laplace domain. So those are some properties, for example. But one of the main property is that if you have, for example, a Dirac's delta function in time, so for example, let me write so a delta. So basically, let's assume that you have a disturbance that is acting as a delta. If you do the Laplace transform of this delta, that will be equal to 1. If you have a disturbance that is 0 up to a certain time, so let's say time t0, and so what happened here is that the Laplace transform of this step function that we call u dt, that is important for the next slides. So this one will be equal to 1 over s. But you have also other functions. For example, if you have a step function t, so this step function multiplied by t, this will be 1 over s squared. And you can compute many different expressions. So this slide is only to let you know that a time function over time in the Laplace transform in Laplace domain will correspond to this one. Usually, what is used, you have tables to look at what a specific function is in a time domain, and so you can directly transform that in the the same function in the Laplace domain. I've said that, that is only for your better understanding when we are going to introduce the Laplace function, the Laplace transform. Let's start to analyze this dynamical system. So as I said, what we are going to start with will be indeed the pitch dynamics. So before going to each single equations, an additional representation that is usually used is the coefficient sigma y, sigma x, and sigma z. These coefficients are only related to the moment of inertia of the spacecraft and will play a major role to determine the stability. Because as you can already understand here, the stability of the spacecraft will be only driven by the value of the moment of inertia of the spacecraft. So let's start with the pitch equation. And from here, we can already determine some important conditions. The first important condition here is that if you apply the Laplace transform to this equation, so you will have here s squared plus 3 omega 0 squared times the moment of inertia, because as we said, the theta is not multiplied by, is basically equal to, you don't have any additional Laplace coefficient here. So what we are going to have here is this characteristic equation, and assuming that, for example, T dy is equal to 0. So we are considering only the associated homogeneous equation. Well, the first thing that you have to know is that, of course, in order to have a stable solution, S squared should be less than 0. Because we know that if we want to have stability, if we have that S is a real number, there will have a positive and negative value. So we have to be careful that there will be an imaginary number. And so basically that our response will be a cosine, a sine terms. In order to have that, you can easily check that the moment of inertia along the roll axis has to be greater than the moment of inertia along the yaw axis. So basically, this term here has to be greater than 0. This is something really well known, and also we can easily understand that here we don't have any damping coefficients, so we only have an oscillation pattern that with a specific frequency that is related to the orbital frequency of the spacecraft, and also the parameter sigma y, since we have defined sigma y as indeed yx minus yz divided by iy. So what you have here is the frequency at which your oscillation in the pitch angle will be. So let's assume that you don't have any disturbance, but you have only an initial angle, for example, theta equal to 1. The response of your system will be an oscillation with this frequency. We are going to see these examples with MATLAB script in the second part. As I said, this is only a theoretical approach. So now we have to deal with the roll and yaw axis. The main problem here, as you can see from the equations that we have written on the right side, is that we have these coupling terms. So we have this term here and this term here. In order to integrate these equations, so in order to know the stability of these equations, we have to analyze these equations together. So first of all, what it is done here is to use this representation, and it is the representation that I've also used in the MATLAB script that I'm going to show you later. So what you need to do is basically to define a vector that you want to integrate. So in the general case, what you do is you define a vector of angles given by phi, theta, psi, phi dot, theta dot, and psi dot. And you have this 6x1 vector that you want to integrate in OD45, for example. Here, the problem is reported in the 2D, so we are ignoring the pitch because, as I said, is completely fully decoupled. If you basically use these for this representation, you can then write a matrix. So from here, you can indeed determine these matrix here. So you will have phi dot, psi dot, phi dot dot, and psi dot dot equal to a certain matrix that depends on the coefficients, but it's really simple to show, times the other vector. So basically you have phi, psi, and phi dot, and psi dot. So now we have to find out this matrix that is in the next slide. It is easy to demonstrate, of course, the first two rows means that phi dot is equal to omega phi, so it is really easy to understand. And the only terms that you have in this matrix depends on the frequency of your orbit, and the sigma, that is the term related to the inertia, moment of inertia of the spacecraft. So in this case, it will be term Iy minus Iz divided by Ix, and this will be Ix minus Iy divided by Iz. So what you need to do here is to find the solution of this equation. Well, what you can easily see here is that we are going back to the to a problem of eigenvalues of eigenvectors. So you can easily demonstrate that if we want to determine the solution of these equations, a convenient form would be to have a diagonal matrix here. How we are able to do that? We are able indeed by approaching the problem by using the eigenvalue eigenvector problem. So by using a minus lambda I equal to 0. So in this bottom part of the slide, we are introducing a vector y that is equal to the vector x that we have defined here, multiplied by m, where m is equal to the, as written here, but is basically the 4 by 4 eigenvectors of the problem that are called u1, u2. So let me clear that. So let's go back to this one. So you can see here that you have u1, u2, u3, and u4. So if you multiply that x to the out of eigenvectors, you are able to invert this expression, so you can compute x as a function of y. We are going to do that because our final goal here is indeed to find an expression that will have basically y dot equal to a diagonal matrix lambda times y. So what we are doing here is multiply. So since we know that x is equal to the eigenvector matrix, the inverse of the eigenvector matrix times y, we can substitute that in x dot and x. So you find that m minus 1 x dot is equal to ax. But x can be substituted by this m minus 1 y. And so at the end, what you get here is that the y dot is equal to m, so the eigenvector matrix times a times the eigenvector matrix, the inverse of the eigenvector matrix times y. So in the next slide, you can easily see that this matrix here is the eigenvalues matrix. So we are able to transform the matrix from the the matrix that is not diagonal A to a matrix that is lambda. And we know that these second order equation can be solved by using a sum of functions that are dependent from the exponential times lambda, that is the eigenvalue, times the time. So what we are going to do basically is to see that our solution depends on the eigenvalues of the matrix A. So the main problem here is that afterwards we need to go back to X, of course, but this transformation is straightforward. So if we multiply this psi I, the exponential term, by the eigenvector matrix, we are able to see that X is a function of this exponential term that depends on the eigenvalues. Well, so now we have to discuss something that is already clear for you, but basically this approach gives you the basic idea to understand why, when we have this stability. So the stability of the system will be demonstrated only if lambda will have, so the characteristic equation basically has complex conjugate solutions. So as we have seen for the pitch angle only, if lambda in the problem of the roll and the axis have complex conjugate solutions, also in this case we are going to have an oscillatory behavior. But if those eigenvalues of the equation, previous equations, have a real and positive part, the system will be unstable. We're going to see in the next hour what are the condition of stability and instability. So here we only demonstrated that we can determine the eigenvalues, but now we need to determine indeed using the Laplace transform what are the conditions for stability. So what we are going to do in the next hour is to reapproach the same equation and see that in the Laplace domain you can do exactly the same thing. The only difference here is that you're going to transform this differential equation in an algebraic equation. So the function that you have here, so if you do the Laplace transform of x dot, this Laplace transform is indeed equal to S x in the Laplace domain minus x0, and the Laplace transform of x is directly A, so the matrix A times x ds. So what we are going to have at the end is always a similar problem that we have seen in the time domain. So basically you have that S identity matrix minus A times x ds equal to x0. So in order to determine the response of the system, we know that that is equal to Si minus A, the inverse of this matrix. So in order to compute this matrix here, what we need to do is to compute the adjugate of the matrix Si minus A. The adjugate of the matrix, I reported here an example, is given by, so if you have a matrix 3 by 3, the adjugate matrix means that the first element, for example, is, let me write down here probably. So the first element here will be minus 1 times I plus j times the determinant of the submatrix of this submatrix here. So the determinant of that submatrix. So since I plus j in this case is 1 plus 1, you will have that this one will be positive. And you can see indeed that you have to compute only the determinant of this submatrix. Same story for A12. The only difference is that you have minus 1 I plus j. So here is 1 plus 2. So you have a 3 here. So that's the reason why you have a negative term here. And this is the determinant of this column here and this subcolumn here. So you have to cancel out the first and the first row and the second column. So that's the explanation for this matrix that I also reported mathematically here. But the only things that matter here is that at the end, also if we look at the problem in the Laplace domain, the solution of that response, so the solution of that function should be reconverted in the Laplace, in the inverse Laplace transform. So this formulation that we have seen here has to be transformed in, so with the inverse Laplace transform. It can be easily demonstrated that the solution of the inverse of the Laplace transform of this expression here is given by the sum of the values that are indeed given by xk times the exponential term. So by using this additional term, additional approach, you can arrive to the same conclusion that we have seen before. So the next hour, we're going to see here, so in the next hour, what we are going to see is what are indeed the value that provides stability and what are the values that do not provide stability. So that's the reason why I will show you a MATLAB script that demonstrates what we are going to see theoretically by using this expression. So now let's have a break and we restart in 15 minutes. But let me know if you have. So one of the questions was regarding the stabilization of the space tether. So, and why we are not considering the third equation. So in reality, it's not. So we are not excluding that equation from our analysis. So what the main goal here is to show where the gravity gradient can be useful. So that's the reason why you see that if you have that Ez is equal to 0 because it is a space tether, and you have that Ix and Iy are equal because of the geometry of and the shape of the object, basically the only terms of the gravity gradient that are not equal to 0 are in the roll axis and the pitch axis. So it means that the gravity gradient, so what is called the GZ here, is basically 0. So it means that if we want to use the gravity gradient to stabilize the spacecraft attitude, or actually the space tether attitude, the gravity gradient is not going to provide any torque, basically. And so, so if you have, for example, that even if you have a disturbance here in the z direction, this will be independent from the gravity gradient. So it will start to rotate because of the disturbance, but the gravity gradient will not be able to counteract the disturbance. So that's the reason why what it is written in this right side of the equations is that what are the contribution of the gravity gradient for a space tether? Only in the roll and pitch axis. So we don't have any contribution of the gravity gradient in in the pitch axis, in the yaw axis. But so it doesn't mean that we are not going to integrate. So if we want to know the attitude, for example, of the space tether, what we are going to introduce here, probably that will clarify, is an additional equation T d zeta equal to I. Oh, actually, the problem is that I zeta is equal to 0. So the problem here is that I zeta is equal to 0 as well, because we are considering, I mean, in reality it's not exactly equal to 0, but here basically is equal to 0. So you don't have enough information to determine the attitude, because basically the line is assumed, so basically the tether is assumed to be infinitely thin. But assuming that the space tether indeed doesn't have as a sort of thickness, so the only thing that you can see that the only contribution will be given by the so the gravity gradient will not have a significant contribution to the attitude, to the attitude control of the tether. But as I said, this is only a simplified example, so it doesn't really matter so much. So what we are going to see next will be definitely closer to the reality. So here we are not excluding that, but the fact that the assumption is that the tether is infinitely thin, basically you don't have a third equation, because you're not able to determine the attitude of something that is basically doesn't have a realistic dimension. Okay, so let's go. Prego. So let's go ahead. As I said, I don't want to go back to this, because as I said, this is really something that you already have seen in other courses. So how to deal with the solution of a differential equation, and if you want to see, for example, the modes of the solution. So here we are doing exactly the same. So we are trying to determine the modes of the system by using a classical approach in time, or by using the Laplace transform. What you have demonstrated is that indeed we are going to have exactly the same form. The problem is indeed that we have to demonstrate that those roots of the solution, so the eigenvalues of the problem, if we look in the time domain, should not have a real part, but a real positive part, in order to don't have stability, instability, but we want to have something that is indeed going to provide stability to the system. So let's go back to the problem itself. So what we have here is that we need to determine the eigenvalues of this matrix by using the approach that we have seen, so the first approach. So we introduce these S, that will be our eigenvalues, and we have to solve for the characteristic equation. So what you can see here is that what we need to do is to solve the characteristic equation of the system. So if you compute the determinant of this matrix, you can easily see that you have a characteristic equation of the fourth order. So you need to find the 4 roots. And you have to be careful that these 4 roots indeed are going to provide a stable system. Just to remember is that this characteristic equation is only for the roll and yaw axis dynamical equations. So we are treating the pitch axis separately, because we don't have any coupling of the system. Okay. Before going ahead to determine the roots of this equation here, we need to show some properties, Because what we are going to see indeed is that the stability of the system depends only and exclusively from the moment of inertia of the system itself. One property, one important property is indeed the sigma x, sigma y, sigma zeta. So that will be also true for sigma y, sigma zeta, are less than 1. You can easily demonstrate that if you explicitly determine the moment of inertia of the spacecraft. For example, for sigma x, you can demonstrate that at the end you have an integral of z squared minus y squared divided by the sum of the two. So these demonstrate easily that it is a quantity lower than 1. That will be easier, that will be important later, when we are trying to look at the solutions of a stable system. And so as the same for sigma z and sigma y, you can easily demonstrate that. We can also demonstrate that sigma y is, so that the moment of inertia of Iy is less than Ix plus Iz. So basically, if you took sigma zeta, if I remember correctly, this one is equal to Ix. So let me go back just to see if the signs are correct. Yes, it's Iy minus Ix divided by I zeta. As I said, this is easily to be demonstrated that it is less than 1. So if you took Iz on the right side, so basically you know that Iy minus Ix is less than I zeta. And so it is easily demonstrated that this gives you Iy less than Ix plus I zeta. So these properties of the moment of inertia are fundamental for the later consideration. So what we want to do here is to determine the characteristic equation and the poles of this characteristic equation. So we are dealing with the homogeneous associated with the system. And what we can see is that the roots of this system can be easily computed as s squared divided by omega 0 squared. So we have to be careful that this quantity here has to be negative, for the same reason why also in the pitch case the quantity was, so the s squared was to be a -1, because we need to have imaginary solution. So basically something that will be indeed will provide an oscillatory mode. In order to have that this root, so this root here will be indeed less than 0, we have to consider 3 quantities. So first of all, we have to be sure that the radical, so the square root of this quantity has to be greater than 0 in order to don't have any imaginary number here. So basically this root here has to be positive. So that's the reason why, in order to have that, we have that this condition. So we have a positive discriminant of the system. The other condition is also that the square root of this term, so what it is here, the square root of this term here has also to be positive. And that's the other condition. So we already found two conditions. Those conditions will be important because what we are going to do indeed will be to find the configuration of sigma x and sigma zeta, then provide stability. And as I said, these parameters depend on the moment of inertia. So we have to find all the conditions that give you the sigma x and sigma zeta configuration to for stability. The third one is even simpler, because basically this part here has to be positive in order that the minus give you a negative numerator. So this condition here give us three conditions for the poles of the solutions in order to have the negative, so that s squared is negative, and so that will provide oscillatory behaviors. Well, another condition comes from the pitch stability. So now is the first time that we're going to couple the stability given in the roll and pitch, in roll and yaw axis with the pitch. So an additional condition, as we have seen before, was that Ix has to be greater than I zeta. So the moment of inertia along the roll axis has to be greater than the moment of inertia of the yaw axis. That was, for example, verified for the tether. We're going to see that with examples, so those values will be clear later. But the other condition that we have to find here, that we have demonstrated before, is coming from sigma zeta that is less than 1. And this one give you this condition here. So this is indeed the sigma zeta, it's not the sigma x. Sorry about that, but let me correct. That we have demonstrated before. So what we can do here is to find an additional condition. So in order to go directly to the final point here. So the final conditions that we have to take into account, as I said, so this one is coming, so this condition here is coming from sigma zeta less than 1 gives you that. Now we can indeed convert this condition here in sigma terms. So if you multiply both terms of Ix minus Iz, and that could be done, so you are able to do that only because we know that Ix has to be greater than Iz. So because of pitch stability, we know that this quantity is greater than 0. So we can do that, and we can combine these two relationships in the final relationship that sigma z has to be less than sigma x. So by transforming, so we have multiplied this one by Ix minus I zeta. So basically we did here Ix minus I zeta times I y less than, basically you have, since you are doing the same, Ix squared minus Iz squared. We can do that only because this property here is verified. So by basically transforming a little bit the commutating the terms that you have in this inequality condition, you can finally arrive to that formulation here. Okay, so let's recap that so we can go to the examples.
Scusi.
Prego.
C'è un piccolo errore nella slide precedente, se non mi sono sbagliato a vederlo. Quando si raccoglie l'ultimo passaggio, IZ dovrebbe esserci al secondo membro della disuguaglianza Y meno IZ, perché prima c'era un quadrato con Z quadro.
Grazie, grazie. Ah, ecco perché non posso, perché queste non posso cambiare. Ok, grazie, lo cambio, perfetto, grazie. So yes, there is an E zeta here, right? Giusto?
No, dicevo dall'altra parte, al secondo membro della disuguaglianza IZ quadro, poi l'ultimo termine all'interno della seconda parentesi. Ci sta IZ che moltiplica Y, esatto. Anziché X si scrive IZ. No, dentro la parentesi, no, come stava facendo.
Ah, ok. No, è che non devo prendere il pennino. Qui.
Esatto.
Ok. Grazie. Poi ve l'aggiorno. Ok, so if you do exactly, so this is a correction to make. So you can find that sigma z is less than sigma x. And so those are so all the five main terms that you have to include to determine the stability of the system. Okay, so let's go ahead, and you can see that the first term here give you a parabolic expression. So you can indeed determine that whatever is inside this parabolic pattern would not satisfy this condition. So you have to delete all the solutions that are within this parabola. We can explicitly write that if you want, but basically this parabola is, so let me write that here. So this one is basically terms of sigma squared times 9 plus sigma zeta squared time plus sigma 6 sigma zeta. So you can explicitly determine what is the parabola. So now I'm not going to write. Okay, let's write. It's another few terms. So sigma x 6 minus 14 sigma zeta plus 1 has to be greater than 0. Okay. So this is coming from the first condition. Okay, from this one. The second condition, sigma x greater times sigma zeta greater than 0, that was this condition here, give you tends to exclude all that region that is above the line sigma x equal to sigma zeta. Actually, not, sorry, these exclude only the fourth and the second quadrant here. The line that you have here is given by the final property, the final condition that we have found here. If you look at this one, you are able to exclude all the terms that are larger than this line here. So sigma x equal to sigma z. The second property exclude the fourth and the second quadrant. So at the end, what are the regions that are remaining for stability, possible stability of the spacecraft? These part of the first quadrant, that is called region A, and the very small part between the parabolic trend and these upper triangle. So you have this B region here that is called the Brad-Delpa region. However, both regions have problems in stabilities related to the design of the spacecraft. As we are going to see in the exercise in MATLAB, what you're going to have is that basically the stability that you need to have here, so that the sigma x, for example, has to be greater than sigma zeta, give you the relationship of that I y has to be greater than ix, that has to be greater than I zeta. So this relationship is coming from the stability of the pitch axis. This one is an additional relationship that is coming from the fact that we have seen that the stability of the system is only valid if we have the sigma x is greater than sigma z. Okay? So the other property, however, is not the only property that we have, but we have also demonstrated that since sigma zeta by definition is less than 1, these give you that Iy minus is less than the sum of Ix plus Iz. And this will be a tight, will provide a tight constraint in the design of the spacecraft. So that means that we have demonstrated that the stability of the system can be achieved by developing the spacecraft in a way that the moment of inertia of the spacecraft will be aligned to the pitch and roll axis, pitch, roll, and yaw axis in the way that we have seen so far. So we need to find a geometry of the spacecraft in a way to get basically that the moment of inertia will help through the gravity gradient the stability of the system. So it means, for example, that the figure that we have seen previously here is not a case that this box here, this bus of the spacecraft is designed as it is in this figure. This figure has indeed that the moment of inertia along zeta is less than the moment of inertia along y and along x. So in order to have stability, especially for the pitch angle, you need to have that Iy, so Ix has to be larger than Ix. But also if you want stability in the roll axis, the moment of inertia along y has to be greater than the moment of inertia along zeta. So that's the reason why you have this shape here. And the main important thing here is that you have a direct relationship between the three moments of inertia to know from the beginning if you are going to have a stable satellite because of gravity gradient or not. There is a caveat although what we are seeing here is valid only for small angle approximation. So we are assuming that our body frame is very close to the orbital frame. In real cases, this is not true. So what we are going to see by the example that are reported after that this slide here is that we need to deal with when these conditions are not valid with the entire, so with the full dynamical equations that is reported in this case here. So to explain what we've seen so far, and the similar consideration can be done for the B section here. The only difference is that you can see that the order of the moment of inertia is different. So the minimum moment of inertia will be Iy, but that of course will provide a lower, so that will be a region that will not be really physical, because basically will require extreme constraint on the design of the spacecraft. Let's try to do some examples. So the example that you can find in the book that is suggested, so the CD in chapter 5, I did basically, I used the values that were done in this chapter just to show you, for example, how we are able to determine the stability of the system. So let me show you the MATLAB script. So the MATLAB script is very easy. You can do by yourself, but what you need to do is to define the moment of inertia, a certain angular velocity of the orbit. For example, the example that we're going to see is considering a circular orbit at 800 kilometers. That corresponds in a radian per second of omega 0 equal to this value. Let's start by assuming that you don't have any torques, so that the disturbance associated to the roll, pitch, and yaw axis are 0. And you also assume that the initial condition that I can write here probably. So those initial condition, so the vector that you have here is, as I said before, a 6 by 6 vector, 6 by 1 vector, sorry, in which you have phi, theta, psi, phi dot, theta dot, and psi dot. So you need to integrate a 6 by 1 vector, and the initial condition here is that you don't have any roll angle, you don't have any spin along the roll axis, and you don't have anything for the pitch, but you have an initial angle psi for yaw. As I said, this is pretty straightforward, because I wrote a subroutine ELV that you can indeed use, in which I computed the dynamical equation expressed by assuming the small angle approximation. So it's the equation that we have seen so far. In the book, the same example is done by using the full non-linear differential equations. So there is a big difference, because when we are going to deal with small angles, the two results will be identical. But when, for example, the system will be not stable and we are going to diverge, this equation will be accurate and will show you what actually will be the response of your system. The equation that I've written will be close to the reality only for the first period before it's diverging for a larger angle. So you can easily see that here the first three elements are phi dot, psi dot, theta dot, and psi dot. And these are the acceleration, the angular acceleration expressed in terms of the disturbance and the angular velocity of the spacecraft and the moment of inertia. Let me know if you want to know something else, but this is a really simple program. It's only to show you what we have seen so far.
Scusi,
So let's done. Prego, prego.
Fare una domanda. Tutto lo studio di stabilità che abbiamo fatto fino adesso, teoricamente è in assenza sia di gradienti di gravità che di disturbi, giusto? Cioè sono soltanto l'omogenea associata, diciamo.
No, il gradiente di gravità c'è. se no, se il gradiente di gravità fa parte già dell'equazione. So the question is, if we are assuming, if we are studying the system without disturbances, this is true, but with the gravity gradient. The gravity gradient terms are related to the terms with omega 0. Okay? So the gravity gradient, so the reason why we linearize the system here is that if you have that your body frame is close to the inertia, the orbital reference frame is moving following the orbital reference frame. So the gravity gradient terms are expressed directly by omega 0 term. So all the terms with omega 0 are the terms that are associated with the gravity gradient. So the gravity gradient is here, and that's the reason why we are studying the stability of the system, because otherwise, if we do not have any gradient, any additional term, the system will be unstable, of course, because we don't have any action from, for example, the gravity gradient. So what we are doing here, so let's start by assuming that we don't have any perturbation. So just to check what we have seen so far. So if we use two different configurations of the same satellite. Prego.
Velocemente soltanto per chiedere, non avevo sentito bene. FD, per esempio, che cos'era? Feed delta, che cosa dovrebbe essere FD? Feed all'interno dello script MATLAB.
Ah, questi sono, ok, so phi and FD so are the
just
is the angle and the derivative, so it should be phi dot.
Perfetto, perfetto, grazie.
Okay, so our phi dot, theta dot, so you can see here is phi, theta, psi, phi dot, theta dot, psi dot. So you have a 6x1 term. Okay, so what I would like to show you is that the first case that is presented here is if you have a spacecraft with a moment of inertia along x 6, 8, and 4 kilogram per square meter. So this is for Ix, Iy, and Iz. We will have a response of the spacecraft. The same spacecraft has also a possibility to have a boom along the y-axis. So we are increasing the moment of inertia along x and y. We are extending a boom along the z-axis. That's the reason why you can see that this boom enables to increase Ix and Iy. Why it is important? Because as you can see from here, the plot on your right side, so the one with the red plot, so it is using the moment of inertia Ix, so 6, 8, and 4. So you can see that if you have an initial angle 5 degrees along the y-axis, you're going to have an oscillation with that amplitude. What is also true is that since the roll and yaw axis are coupled, you're going to have also a variation in the roll axis. And you're going to see this pattern that is given by the relationship between the two. If you have a zoom, z boom along the yaw axis, you are increasing the moment of inertia along the roll axis only. Since we know from the expression that we have written that theta is not really affected by the other two dynamics. So basically in our approximation, theta is still. If we increase the inertia, so the boom along the z-axis, you can see that the variation, the amplitude of phi is indeed going to be definitely lower. So we are able to increase the stability of the system by including a boom. This is a very trivial demonstration. This is only true that we didn't change anything about the stability along the u-axis. And that's the reason why you're still having oscillation. Another thing that you have to notice here is that the solution that you have from my MATLAB program and the one that you have in the slides are exactly the same. Although here the solutions are computed by integrating the full nonlinear differential equations, and I assuming the small angle perturbation. So now let's try to include a perturbation, for example. So let's assume to have a perturbation in the y direction. Let's say 10 to the minus 5. This is a Newton per meter. Okay, so what you're going to see, probably I choose a value that is too large. And I'm not able to. Let me choose a smaller value, let's 10 to the minus 7. Okay. You can see here, I have the problem that the MATLAB script is close to Zoom. I'm not able to. Okay, here it is. Okay. So you can see that the red case corresponds to lower moment of inertia along the roll and the u-axis. But the other thing that you can notice is that the oscillation in the pitch angle varies with the moment of inertia along x. So you can see here that not only we have a smaller variation of the angle, but also we are going to have an oscillation with a larger frequency compared to what we've seen for the moment of inertia, a lower moment of inertia. So the red one are with lower moment of inertia, the black one with a large moment of inertia. So if we look back at the slides, we have seen that indeed the frequency directly depends on the sigma y. That's the reason why if you have a larger Ix, so basically a larger, you can compute that varying the moment of inertia, you're going to have different frequency in your system response. So now we are looking at the stability of the system, that is true if you have a constant, if you don't have any perturbation, or if you have perturbation. The criticality of this system is important. So the other case, for example, is if you have a torque in the roll direction. So what I would like to demonstrate is that the gravity gradient is and could be enough to stabilize the spacecraft if you have torques along the roll and the pitch axis. But if you have a torque along the theta axis, you're not able to have a good response from the gravity gradient, because the gravity gradient will not provide a significant response. So let's do for this one and this one. You can see here that for this moment of inertia, so the lower moment of inertia, so this is for t zeta, let me write t dx, those are t dx equal to 10 to the minus 5 Newton per meter, okay? And this is with the lower moment of inertia, this is with the large moment of inertia. You can see indeed that you are starting to diverge for the lower moment of inertia. So this integration is not really true. It's something biased because we are considering a small angle approximation. In the case with the Z boom, you can see that indeed you are able to have, you can still in this small angle approximation. And if you compare this plot with the one that you have in the slides, you can see that you have a similar trend. Although here, okay, it's not identical because I think that in the book they started from psi equal to. So let me cancel this one. Okay, so you have to compare this one with the one. So if you have indeed TDX equal to 10 to the minus Newton per meter, you have exactly the same solution if you use the full dynamical equation or not. So it means that if you have enough large moment of inertia of the spacecraft, you are able to provide stability in the roll and pitch axis. But in the yaw axis, of course, the problem will be definitely critical. To do this example, we can indeed consider the perturbation along the z direction. Okay, so let's compare this plot with what you have in the slides. So if you have, for example, a perturbation, a constant perturbation along the z direction, what you can see here is that if you propagate the state by using the real angular equations, so Euler equations, you can indeed have this pattern. What I have here is completely different because the problem here is that the torque that is applied to the yaw axis is not balanced or is not probably balanced by the gravity gradient. So after a few seconds, the angle psi is going to be so large that our small angle approximation is not valid anymore. If this is not valid anymore, the three equations for roll, pitch, and yaw will be strictly coupled. And that's the reason why what you're going to see is that the phi angle will diverge and also theta, because when you're going to use, if you use the full dynamical equations, the coupling for larger angles becomes important. And the yaw axis is not indeed diverging, as you can see from this simplistic approach, but actually is going to oscillate. So what is the problem? What we have emphasized today is that the gravity gradient, the passive stability, is not enough for the yaw axis. We need to provide an external tool. And also for the pitch and for the pitch and roll axis, you need to include additional actuators in order to dump or to mitigate these errors. Because, for example, in this case, you can, for example, if you have, as we have seen, Tx equal to 10 to the minus 5, you can accept, for example, an error of 2 for 4 degrees in the roll axis. But in reality, you want to have something that is closer to 0. So you need to activate your actuators in order to provide a 0 error, a 0 control error. So what we are going to see next week, we are going to start with the actuators that are applied to this passive stabilization. So wheel dampers and magnetotorques. So those actuators enable to dump this oscillatory behavior. And afterwards, we are going to see the other two main actuators. They are the thrusters and the reaction wheels that will provide the possibility to determine, to control the attitude in 3 dimensions. Another thing that I would like to point it out before the end is that if you compare the slide that you have with, for the case TDX equal to 10 to the minus 5, in my plot, you see that theta is equal to 0. It's not changing over time. Well, the reason why is because since I'm using the small angle approximation, you can already see that when you have a couple of degrees for psi and phi and phi, theta is going to be coupled with the phi and psi. So the small angle approximation is not valid anymore. That's the reason why the integration of the full nonlinear equations is definitely more important. So how to avoid this problem? The problem could be really avoided if you keep your attitude, your control, your attitude closer to the orbital frame. If you always are able to keep that close, the equations that I have written are enough accurate. So I would conclude with that. And next week, we are going to start with the actuators that indeed enables the control of attitude of the spacecraft. So let me know if you have quick questions right now.